So far, we've used integral transforms to solve the idealized waveguide and the Pecoris waveguide, and we found the pressure fields, and both of those solutions were summations of modes, right? So I want to talk a little bit more about properties of modes, and we ended the last lecture talking about, or maybe it was, 2 lectures ago, talking about the propagation angle of modes, in the sense that we could represent each mode as upward and downward traveling plane waves. So along with that, we can also represent those upward and downward traveling plane waves. Let's do a drawing here. Right, so we have our source somewhere here, and we're saying here's our mode. This particular mode is going to have some associated angle alpha, and by summing an upward and downward traveling plane wave at that angle, you get the right interference pattern, okay? Now we can also think about this mode as having 2 different properties. In the horizontal, it can propagate energy, right? And so when it's propagating energy in the horizontal, we call that the group speed, okay? But it also has phase speed, which is the speed at which this particular phase travels in the horizontal, right? This particular phase of the plane wave. Okay, and of course it has a speed c, which is 1500 meters per second, the speed at which the wave travels through the medium. Okay, so what are the relationships between all these things? Well, let's look at that in a little bit more detail. So let's examine the dispersion relationship. Okay, so where do we start with the dispersion relationship? Well, relationship between frequency and wave number. So we have this nice little wave number relationship we can also use in our waveguide, right? K is equal to kr squared plus kz squared. This is in the cylindrical case, right? Could also be kx squared plus kz squared, the square root of that, in the 2D Cartesian case. So when we plug that in, we get this nice expression. And let's just consider the idealized waveguide for now, okay? Kz equals m pi over h for idealized. Okay. So the horizontal phase velocity is simply given by omega over kr. That's going to be a horizontal phase velocity. And so this is, the horizontal velocity of a particular phase in the plane wave representation of the mode, right? So exactly as I've drawn here, the phase speed is this horizontal velocity of a particular phase. So this is not the energy. Particular phase of the plane wave. If we're interested in the energy, we have to talk about the group speed. So you might be thinking maybe back to a physical oceanography class, I know what the expression for the group speed is. Where does that really come from? So let's look at our case here. Since we're talking about energy flux, right? So if we go in the time domain, we look at our pressure field in the time domain, right? In terms of r, z, and t, we can say it's going to be some integral of our frequency domain solution over some bandwidth, right? Which I give by omega minus epsilon to omega plus epsilon. Here's the solution that we actually derived, right? That's our modal solution in terms of frequency. And then we're going to do our inverse transform, and it's going to be omega t minus kr, and I put the m there because really we're talking about a discrete modal solution, right? This p here, p of omega is a modal solution. So in a time t, dt, let's say, in a time dt, the signal propagates dr equal to um dt, okay? So for the signal to be unchanged during dt, the phases must not change, right? So we actually need this whole expression here to be unchanged. Wow, I'm already running out of room. Not even on the board, and I'm running out of room here. So, okay, let's just go, let's take this over here. And we can say, all right, well, if we have d omega dt minus dkrm dr, that whole thing equals to 0. That gives us this nice expression, dr dt equals d omega dkrm, right? So that's going to give us our group velocity, right? This is probably, you're somewhat familiar with this expression from physical oceanography, looking at surface waves or even internal waves. Oops. Did I get on the right page here? Let's go back. Okay, so group velocity. It's just kind of nice to know where it comes from sometimes. Nice to write it down. So group velocity is given by, now equals d omega dkr. So that's going to be d by dkr of c times our nice little substitution, m pi over h squared. And then we can just simply do that integral very quickly. We get c times kr. Now we're going to have a minus 1/2. And so we get square root of kr squared plus m pi over h all squared in the denominator. Okay? So that gives us our expression for the group velocity. And from the last page, our phase velocity, we can just plug things in. We're going to have kr squared plus m pi over h squared all in the numerator now over kr. Now there's two ways, of course, you can think about this. The group velocity is the slope of the dispersion relationship, right? You've probably seen this in terms of surface waves in PO before. But so that implores us, well, let's plot these things, right? So we want to plot them here as velocity. This is going to be 0, increasing velocity. Sorry, not 0, 1500. Okay? And what do these two things look like? Well, they both, let's actually just look a little bit closely before we sketch them. Let's just look a little bit closely here. So as kr goes to infinity, or gets very, very large, right? Why is that interesting? Well, as kr gets very, very large, we're talking about k squared minus m pi over h squared getting large. And of course, k squared is really related to frequency. So we're basically talking about for large frequency. And if you look at the expression there, you can see, okay, well, you have a kr on top, you have a kr on squared on the bottom. So really this thing, is just going to go to c, okay? Can we make the same argument for VM? So you're screaming so loud I can almost hear you back in time here. Yes, right? So VM goes to C as frequency gets large. So we know that curves are going to asymptote towards this 1500 meters a second, or really this is C, right? And so then you can see, okay, well, what happens as we go down in frequency? And I should label this axis here, shouldn't I? Well, so for VM, we're approaching C from above, and we have sort of, it's quite easy to see that as you go down in mode number, you get closer and closer. You can support lower and lower frequencies. So there's our increasing mode number, V1, V2, V3. And similarly, U1, U2, U3. So the interesting thing here is, of course, that the phase velocity basically is going to 0 as you go down lower in frequency. And I think this goes back to this idea of angles. Pretty easy to understand, I think, if we think about our plane waves, right? So VM really is the propagation in R of a fixed point of phase in that plane wave, right? And the angle of propagation is related to the mode number. And so for low modes, or for, actually mode number not really important, but let's just consider this one particular mode here. If we think about this angle getting steeper and steeper, right? We can see that for each little bit of propagation in the direction of travel, there's a larger bit of propagation in the of that point in phase in the direction of R, or the horizontal direction, right? And eventually you get to a point where if you have a wave propagating straight down, it's actually your phase velocity is infinite in the horizontal, right? So that's the idea there. And conversely, as you get to a shallower angle, right, your phase velocity approaches the actual velocity of propagation in the medium, C, right? So you're going C in this direction at all times. And this other arrow is your phase velocity. Okay. So the interesting thing about the group velocity is that modes have characteristic speeds, right? So this is a really useful bit of information, and we'll just talk about this from an experimental point of view. So you have your waveguide, you have some source, it turns into some modes. At first all the modes are sitting on top of each other, right? But as it propagates out, you recall that our diagram of mode speeds, where this is C, right? M going this way, U1, U2, U3. So for as, if we have some receiver out here, let's say we have an array of receivers out here, we can look at a particular frequency, and then we can see that will have mode 1 arriving with a velocity very close to c. Mode 2 is slower. Mode 3 is even slower, right? This is, let me just relabel these, of course. Velocity and frequency. And so as time goes along, or as the signal propagates in range, you're going to have first mode, right? It's got the fastest group speed. Second mode. And third mode, just as we've drawn here. And so now if you just have one receiver here, you're going to see those modes arrive. If we just talk about a time signal, right? You might see those modes, mode 1 arrive, mode 2. Well, I've already made mode 2. I've already made some assumptions here. Let's say all the modes are the same. So you might see mode 1 arrive, and then mode 2 arrive, and then mode 3 arrive. And so if this is your time series here, pressure, time, and you're able to pick out m equals 1, m equals 2, m equals 3, and these are different times, so now we'll say t1, t2, t3. You can just use some very simple equations like v equals r over t, where where v is really equal to right? And so u1 is going to be equal to r over t1, u2 is going to be equal to r over t2. And by using your known dispersion relationship, you can actually compute from these series of equations r. And so that allows you to range your source, which might be at an unknown range, and people have done this for whales and explosions and other things. Now, the other thing that people like to do is something called mode filtering, and this is more when you have a vertical array. It's another way of, maybe this is a pretty idealized picture over here where I'm like, oh, you can see the modes in the time domain. Yeah, you can see the modes if you take a Fourier transform, and sometimes it's actually a pretty difficult thing to do, and people employ all sorts of techniques to pick out the modes. But if you have an array, you can actually do something called mode filtering. Basically, you're looking for the arrivals on this array that have the pressure distribution of the modes. So, this one will have the largest signal at the center. Mode 1 will have the largest signal at the center element, and a smaller signal at the top. Mode 2 will have 0 at the center element, the largest pressure signal, at the quarter depth mark, etc., etc. So you can come up with clever ways to mode filter, and then you can use that to do the exact same thing, estimate the time of arrival of each mode, and then back calculate R. Okay, we're going to leave it at that for modes, and this is going to be just a very short lecture, and we're going to talk about the generalized solution coming up next.